Now let us come to the second point, Ohm's law. Students, just now I have told you the cause of current or the cause of the charges flow is your potential difference. Then the question is, if the potential difference is very large, if the potential difference is high, then the amount of the flow of charge will be definitely high. So the simple law is suggested by Ohm, that is called your Ohm's law. It means if across a conductor the potential difference, if you increase, then the value of the current will increase. But there is a linear relationship between these two. Means V is proportional to I. That is actually your Ohm's law. There is a linear relationship between V and I if you plot a graph. Clear? So if you combine these two, V is proportional to I, which implies V is equal to one constant R into I. Clear? So you will see what this R in some later portion. Now let us understand what is Ohm's law. Ohm's law is, if you plot a graph between V and I, you will see a graph will become a straight line. Means there is a linear relation between V and I that is given by your Ohm's law. If you take V in your x-axis and I in your y-axis, then the graph will be looks like this. And for different conductors, you will find the value of theta is different. See, here temperature is a factors a lot. We will see the limitation in later on. So suppose if this angle is theta, then from this graph, if you find out tan theta and the reciprocal of it, that will give you the value of the R. Here this R is nothing but called your resistance. Resistance is actually what? Literally it is the opposition offered by a conductor or a material to the flow of charges through it. We will later on we will see what is the concept of resistance, why resistance would be there. So try to understand. We will be dealing with Ohm's law here only. Ohm's law is a linear relationship between V and I. If you plot a graph between I and V, that will be a straight line and passing through the origin. See, that's why I have written it very clearly. Ohm's law gives you the linear relationship between V and I. That relation is not V is equal to Ri. Someone might question, sir, this is V is proportional to I. We have written V is equal to IR, but this is not Ohm's law. This is Ohm's law. How? The answer here it is there. Because there are some materials, they won't obey your Ohm's law. But still, we can apply the mathematical equation for them. V is equal to IR. It is just a mathematical relation. Clear? That's why it is called, this V is proportional to I is called Ohm's law. V is equal to Ri is not Ohm's law. Clear? Because there are some conductors, for them we can apply the value of this equation, mathematical equation V is equal to IR to calculate the value of the resistance, but they won't obey this proportional linear relation between V and I. Clear? That's why this is your Ohm's law, this is not. And suppose you see, here I have taken current along y-axis, voltage along x-axis. In that case, 1 by tan theta is your resistance. But somewhere suppose you found someone taken V along y-axis and I along x-axis. So in that case, if this angle is alpha, then tan alpha will give you your resistance. Clear? Now the concept arises ohmic and non-ohmic basing on that equation. Ohmic conductor and non-ohmic conductor. Ohmic conductor are those who obey Ohm's law. In general, most of the materials, they satisfy your Ohm's law. There is a large varieties of materials, they obey Ohm's law if the temperature is your room temperature within. There is a range of temperature between that Ohm's law. For most of the material, it is valid. But still, there is certain exceptions. Clear? Still, there are certain exceptions. So let us understand what are the limitations of your Ohm's law. The first limitation is V ceases to be proportional to the current. For a typical conductor, you see the graph, this is the actual graph for a conductor. The solid line is representing, if you plot a graph between V and I across a conductor, suppose you have taken a voltmeter to measure the voltage and you are applying potential difference across the conductor and the corresponding current you are measuring. If you plot a graph to this point, you see the V and I graph are almost linear. After a certain instant, because of the heat production in the material, then this relation is not linear and the graph started to bend here. It's not a straight line. Clear? But the ideal, if this material would have been following the Ohm's law, the graph would have been your straight line, which is marked by the dotted line. But see, this is the theoretical graph and this is the actual graph for a good conductors, for some good conductors. Clear? That's why this is one kind of limitation. From this region, this graph is non-linear. That's why this portion are not following your Ohm's law. There are some materials we found. Clear? Some higher temperature materials obey this kind of behavior. Means they won't obey your Ohm's law and the graph is clearly non-linear. Then the second limitation is that the relation between V and I depends on the sign of V. Try to understand. The relation between V and I depends on the sign of V. What is the meaning of it? Suppose suppose I have taken a conductor. Let's say, suppose I am taking a conductor. Let's say this is the conductor. The end is A and this end is B. There is a battery. Here is an ammeter which will measure the current. I am taking a voltmeter here that will measure the potential difference across the conductor, and this ammeter will measure the current across it. So let me explain you. This is the negative terminal of a battery and this is the positive terminal of a battery. It is a variable battery. I am just changing the voltage and measuring the corresponding current here. So the voltage measurement is done by this voltmeter and the corresponding measurement of the current is done here. So once what I am doing, the positive end is connected to the end A of the conductor and negative end is connected to the end B of the conductor. So in that case, let us say the graph, in that graph, let's say V is the positive direction and I is your current in that axis. So if you plot a graph in the forward direction, what you are getting? The graph almost is constant to this point and the graph is non-linear here. Now the second case is, if you reverse, means if the end B is connected here and A is shifted there, then you will see the graph, in that case there is a change in graph. Like you will see the graph will be like this. These two graphs, they are different, they are not same. Means on changing the sign, the nature of the graph is changing for the materials. And also the graphs are non-linear. They are not obeying your Ohm's law, they are not straight graph. And the material, for that material, the graph, this means the graph belongs to a material that is called your PN junction diode. So for a PN junction diode, the IV characteristics or the IV graph looks like this. So this graph, it is clearly not obeying your Ohm's law. Also, if on changing the sign, the relation between V and I are changing. You see, here the graph is here till certain value of the voltage, the current is 0. But in the negative side, it is the negative side of the voltage. You see the graph has started increasing from the point 0. And here you see the current, it is actually given in milliampere and here the current in microampere. There is a huge difference. So this class of conductor means actually it's a semiconductor. This is not obeying your Ohm's law. That's why the relation between V and I depends on the sign of V. If the V sign is positive, positive means this is the connection. V sign is negative means you just change the polarity. A is connected, A just you flip. Means the side B will come here, A will go there. Clear? This is the second limitation. Now the third limitation is the relation between V and I are not unique. Means if it would have been unique, then for a particular value of V, there must be a particular value of I. There is a class, it is again a semiconductor gallium arsenide. So there is a material. If you plot a graph between V and I for gallium arsenide, you see the graph looks like this. Here, this is the graph of gallium arsenide, VI characteristics of gallium arsenide. So this graph we can see. I have make three parts of this graph: part 1, part 2, and part 3. What is the distinction between these parts? In the part 1, you see the graph is almost linear. Means this is the region up to which the Ohm's law is obeyed. And you just see the second region. The second region is your non-linear region. Non-linear region means here if you increase the value of V, the current is increasing, but the relation is not linear between them. Means it is not a straight line. Clear? In this region, Ohm's law is not obeyed as the region is non-linear, but V is proportional to I. Means V, if you increase V, the value of I is increasing, but not a linear relationship, not directly. So that's why it is called non-linear region of the graph. Now the interesting part here, you see here, after this voltage, if you increase the voltage, you see the value of the current is decreasing. Try to understand. Try to understand. Suppose, let us take a line here. For this point and for this point, all you just see this. There are two different points. You see here, this line corresponds to a particular value of the current. But for this point and for this point, the voltage have different values. That's why the VI relation is not unique here. Ohm's law is suggesting for a particular value of V, there must be a particular value of I. But here what is happening? There are two different values of voltages for a particular value of current. That's why there is the unique relation between V and I is not being obeyed here. And the most important part here, Ohm's law is suggesting with the increase in voltage, the value of the current should increase. But here what is happening? With the increase in voltage, the graph is decreasing downward. It means this is the portion where you will be getting the resistance will be negative. That's why this region 3 is called negative resistance region. So these are the three limitations of your Ohm's law. Means that's why these devices, the materials, they are called non-ohmic conductors. Clear? Thank you.